Okay, so we are talking about the closure properties of CFLs. CFLs are closure properties. CFLs, like if we have given two L1 L2, then we have seen in the last class that L1 intersection union is also a CFL. If these two are CFL, and we have seen L1 L2 are L2 is a CFL, and we have seen that intersection need not be a CFL. So, CFL is not closed under intersection. So, for that we have taken one example where the intersection is not a CFL. So, we have taken L1 as A to the power I, B to the power I, and C to the power j, where I is greater than or equal to 1, j is greater than or equal to 1. So, this is a CFL. Why? We can have a grammar for this. We can construct a grammar for this, like S is going to A B, and then A is going to A B and or A B, and B is going to, this is C B or C, small c. Okay. So, if you follow these rules, this is the grammar G which is having these properties. If you follow this rule, you can see this is accepting the all the strings of this. So, this is a CFL, because we can have a context free grammar which can generate this. And also we construct another, we take another L2 which is also a CFL. L2 we take like this, A to the power I, B to the power j, and C to the power j, where I is greater than or equal to 1, j is greater than or equal to 1. This is also a CFL. We can easily construct a grammar for this. I have the example. So, if we take S is going to C D, capital C, and capital C is going to A C A, capital C, and D is going to, this is B D small c or B C. Okay. Now, if we have this one, then we can easily check it is generating the grammar like this. I mean, it is generating the string like this. So, it is basically the generating this grammar. So, if this is our G, then L of G is L2. So, that means this is a CFL. Now, what is the union or intersection of this? Now, intersection of this is nothing but L1 intersection L2 is nothing but A to the power I, B to the power I, and C to the power I, where I is greater than or equal to 1. Where I is greater than or equal to 1. So, this we have seen, this is basically of the form that this we have seen, this is not a, so this is a L, this we have seen not a CFL. Why? Because for this we have used what is called pumping lemma for CFL. Pumping lemma for the CFL. So, let us just recap the pumping lemma. So, if we, this is a necessary condition to a grammar to a language to be a context free language. So, if we have say let us just recall the pumping lemma for CFL. So, given a language which is a CFL, be a CFL, then there exists a n such that if we choose a string from this, I mean if we choose a string from this gamma such that length is greater than n, okay, then we can write this string as u v w x y, where this is this and this u and v and x must be greater than or equal to 1, and this one must be v w x must be less than or equal to n. Okay. So, this is the, and the total is greater than n, the total length. These are all substring of the string. Now, so there has to be n. So, we assume, so suppose this is, we assume this grammar is, this is a CFL. Let us assume, suppose this will reach over a contradiction. Suppose L is a CFL. Then there has to be a some n exist for this, where if we take any string of length more than n, that should be written as this, and this is telling we can pump here. This is telling u v to the power I w x to the power I y, this must also belongs to L, and this is true for all I greater than or equal to 0. That is the property. This is the necessary property for a grammar to be a CFL. So, suppose this is a CFL, that means there exists a n, there exists a n. So, that n we choose to be, I mean any n will work. Now, we choose a z which is more than n. So, we can took a to the power n, b to the power n, c to the power n, this is also belongs to L, and this length of this is 3 n which is greater than n. So, this we want to write in u v w x y. Okay. So, now this must be v x must not be an empty string, and this length must be less than n. Now, from here what we can say? We can say this v and x both are not belongs to c and a and c, because if v is belongs to a and the x is belongs to c, then the length will be more than n. So, they are either in a b or b c. So, if they are in a b, then if we just put this I is equal to 0, then u w y, this will be not of the form of a to the power L, b to the power L, c to the power L. So, then this only belongs to L. So, there is a contradiction even for I is equal to 0, then this is not a, this our assumption is wrong. So, this language is not a CFL. So, that means this given a, so intersection is not always a CFL of given to CFL. We will take more using this property, we will have more examples, but before that let us just see where this can be a CFL. I mean given, suppose let L1 be a regular language, need not be a CF, a regular language means it is CFL, but not all CFL is a regular language, and L2 be a CFL. Then we will see if L1 is also CFL, we know intersection is not a regular, but if one is regular, another one is CFL, then intersection is, then L1 intersection L2 is CFL. Okay. So, this proof we will do now. So, we state this in the last class, we have not proved that. So, this proof we will do here. So, intersection of a regular language and a context free language is a context free language. So, let us try to prove that. So, L1 is regular. This implies we have a DFA for this, say A, q a sigma delta a, and P 0 is the starting state of this DFA and final state FA. Okay. And L 2 is a CFL, that means there has to be a context free grammar which is generating this. That means there should be a PDA, push down automata, which is accepting this either by the means of final state or by the means of empty stack. So, we will here take about final state. So, that means we should have a M PDA M such that this is q m sigma, sigma is the input alphabet, this is delta m, q 0 is the starting state, z 0 f m, f m is the final state of the PDA. So, we know this is accepting by the means of final state. Okay. Now, using these two we want to construct a PDA m prime which will accept this. So, this is a R which will accept, this is a L which will accept the R intersection L. So, basically we will take the intersection, I mean we will run this, we will take the state intersection Cartesian product. So, for the new PDA, that is I am giving you the idea of this. So, for the new PDA we have this yeah. So, let this is our q a cross q m. So, it is a Cartesian product and this is sigma is same and the stack symbol is same, because stack only exists for the PDA, there is no stack concept for the A. So, stack symbol is same and we have to define a delta transition rules and the starting state are P 0 Q 0 and this is the starting stack symbol and the final state is F A cross F M. Okay. Now, the idea is, so we are running these two automata in parallel. So, one automata so the concept is we are running these two automata in parallel. So, this is our DFA and this is our PDA and this PDA we are having a stack over here. And this we have a input, we are running this in parallel. If both are accepting, then we have a AND gate over here. So, accept or reject, this can be categorized by 0 or 1. Okay. If given an input string, if it is accepted by the DFA as well as if it is accepted by the PDA. So, if the both cases it is 1, then it is accepted. If one is accepted, another one, if one is reaching to a final state, another one is not reaching to a final state, then it will not accept. And this is the stack symbol. So, this is the way, this is accept or reject or reject. This is input string. So, one input string will run the automata, I mean finite automata, and we will run the PDA. We for the PDA we take the move for the this is stack also, and then we if we reach to the final state for both the cases, then the answer is, I mean then we will say yes, yes, then it will pass this AND gate and it will say yes, then it is accepted. Otherwise, if one is rejected, one is not accepted, then it will not pass. I mean if one is 0, then this is 0. So, this will be rejected, this is not accepted. So, formally the PDA is like this. So, the delta is, so we have to define delta for this. So, delta of this delta we are going to define. So, delta is input is, so we are taking pair P q, two state, one state is coming for the DFA, another state is for the push down automata. and we have input at f, and we have x is the state symbol. So, this is defined to be a, this is the set of all pairs like this, p prime q prime dot dot dot, where, so p prime is nothing but delta a of p comma a. So, this is a deterministic finite automata. So, you have only one state to go. So, p prime of this, and this q prime. So, q prime gamma, gamma is the, I mean state, see this must belongs to delta m of q a x. So, x is the this symbol. So, that means what? That means we are, say, in the DFA, this is the DFA control. So, we are at P, and in the tape we are reading a say. So, this is reading a, and in the PDA what we are at? We are at Q. So, we are at Q, and our top of the stack is x, and we are also reading this a. So, this is running in parallel. Now, with this move, if suppose this is going to p prime, suppose delta of a, p comma a is p prime. So, that means this will go to next, and this will go to p prime, this control, and here also it will go to q prime, and this will be replaced by gamma. That is the idea. Okay. These two systems are running in parallel, and if one, I mean if both the system are reached to the final state, then only we say this is reaching to a final state. So, this is the rough idea of the construction of this. Okay. So, now we will talk about some applications of the pumping lemma and the closure property mixture. Use of closure property, we can say certain, using the pumping lemma also, certain language are not regular. Okay, say for example, so we want to use the use of closure properties and pumping lemma, both we combine, and we will see some example where we can show certain language they are not CFL. So, we will use the pumping lemma for the CFL. So, let us take an example. So, say W, so it is a coming from ABC such that where W has equal number of A's, equal numbers of A's, equal numbers of B's, and equal numbers of C's. Okay. I mean it is ABC. So, like if we have say A, B, B, A, B, then C, 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 this is belongs to, because how many A's are there? 3 A's, 3 B's, 3 C's, equal number of ABCs. Okay. So, now we will see whether this is a CFL or not. So, the question is whether this is a CFL or not. Okay. So, to show this, we have used the we will see this is not a CFL. So, to prove this, we will use the closure property and as well as the pumping lemma. So, let us try that. Okay. So, how to proceed? Solution. So, we take L1, A star, B star, C star. Now, this is a regular expression, if you recall the regular expression. So, this is a regular language, this is regular set, regular set. That means, any number of A's followed by any numbers of B's followed by any number of C's. So, this is a regular set. Okay. Now, if we take a if we take this intersection with this, suppose this is a CFL. So, we are assuming L is CFL. Now, if L is CFL, then L1 intersection L2, L1 is regular, this will be also CFL, Just now we have seen the construction. Now, what is what is L intersection L1? Now, what is L intersection L1? That we have to check. So, that is nothing but this set. So, L intersection L1 is A to the power n, B to the power n, C to the power n. That we can easily verify. Okay. So, equal number of ones, then this is any number of equal number of A's, equal number of. So, this is any number of A's, any number of B's. So, this will be like this. So, this is basically for n greater than equal to 0. This is the intersection. So, now if we assume this is CFL, then this will be CFL, but this is not a CFL, we have seen using the pumping lemma, but this is say L2. L2 is not a CFL, hence contradictions. We reach to a contradiction. So, we cannot assume this is a CFL. So, this is not a CFL. So, that is using the contradiction we can say this is not a CFL. Okay. Sure. Yeah. Now, we can take other example using the properties, and there are other closeness of the of this using the what is called the yeah. So, we can take another example. We can use the substitution method to see whether a CFL is closed under substitution. We will have a mapping, I mean 0 is going to A, say 1 is going to B, and like this. So, we will have a mapping and we will see that the CFL is closed under substitution. So, let us take another example. This we have seen W is in A plus B star. Okay. So, this is basically pair like this. I mean W is any string, so 0 0 1, then 0 0 1 like this. This is W, this is W like this. So, we will show that this is also not a CFL. So, how we can show this? So, this is basically W is coming from W is any string from AB. This we can write an regular expression A plus B star. This we know, this is the regular expression. Okay. So, how to show this is not a CFL? So, for that we will use that again the same property like a intersection of a regular set and a CFL is a CFL. So, we will check this. Suppose this is a CFL. Okay. Now, we take this A plus B plus, then C plus D plus. This is a regular set. Now, we take L1 which is L intersection, this L intersection A plus B plus C plus D plus. Now, this will be a CFL because this is a regular set and we are intersecting with this with the CFL. So, this intersection will be CFL. One regular set intersection with a CFL is give us a CFL. Now, what is this set? This set is nothing but A to the power I, B to the power j, C to A to the power I, B to the power j, A to the power I and D to the power j. I is greater than 1, j is greater than 1. Now, we know this is not a CFL. So, that means I mean we can use this by substitution method and then pumping lemma to show this is not a CFL. then we can claim that this is reached to a contradiction, that this assumption is a CFL. So, this is not a CFL. So, this is the way we can prove that some of the language, we can take the example, some of the language is not a CFL. Thank you very much.